But recently there are more demonstrations of it in practice. There are many examples, but I'm going to limit the examples that I give you to the recent ones. For instance, in 2017, there was an incident where not just one vessel, many vessels in one of the ports of Russia, they were reporting their location to be up to 20 miles away from their actual location. And this kind of incident happened up to 400 times, which is kind of mind-blowing. And on a more recent incident, because there was some military on October 2021, because some military experiments were ongoing, some of the aircrafts were pushed to the no-fly zone, which kind of shows us how catastrophic the results can be if we do not take GPS security seriously, and it makes us think, is GPS spoofing a new cyber weapon? I want to talk about what GPS is, to give some detail and background about it. It's Global Positioning System. It's one of the many implementations of global navigation satellite systems. And in general, a GNSS system is comprised of 3 segments. The first one is the space segment, where it includes the satellites, well, obviously. And then there's a control segment which monitors the satellites continuously and also facilitates some communication between Earth and the satellite. And finally, we have the user segment, which is like any device that is using GPS for navigation purposes. It could be vehicles, it could be our smartphones or airplanes. There are other implementations for GNSS. For instance, we have Galileo, we have GLONASS, or like let's say Beidou for China, QZSS for Japan, but we are focused on GPS. And when we want to, if we dig into details around GPS, there are different implementations of GPS. We are focusing on that, obviously, because it is more predominantly used. And there are 2 different codes which are very commonly used. The first one is called course acquisition, which is called the L1 implementation, and it is used in commercial off-the-shelf devices. Most of us use the L1 implementation. There is also P code, which is the military one. It is already encrypted, so there is no big security issues around that. We're going to focus on securing the L1 signal. This is a general block diagram of what a GPS receiver looks like. We don't really need to understand everything. There is an RF front end, there is the digital part. What we want to know is that once there are sufficient signals from sufficient number of satellites at the receiver, it performs multilateration and it delivers a solution which is called position, velocity, and time solution. This is called the PVT solution that I'm going to refer to it more throughout the talk. But the main question is, why can't we spoof GPS? Well, first and foremost is that there is lack of authentication in GPS. When they were building the GPS, they were focusing on performance rather than security. That's why it has a trusting nature, and it assumes that there is benign environment. So because of a particular control system, which is called automatic gain control system, which is implemented in almost all of the GPS receivers, it kind of locks onto the strongest signal, so it is sufficient for an attacker to manipulate the signal in a way that it is only slightly stronger than the original satellite signals, and it is going to be able to take over the device. Another reason, which is I think the most important one, is that GPS spoofing is a very low-cost act. Like, we are able to put together a GPS spoofing setup like this with only a few $1,000s. And the software that we need to use is open source, and it really doesn't need a lot of expertise to use the software and do GPS spoofing. That brings me to the particular threat model that we are dealing with. The threat model has evolved through time. The particular type of threat that we are dealing with is obviously a type of attacker that is trying to fuse a false position, velocity, and time on a random GPS receiver, but it is more evolved, so its objective is to cover as many users as possible, and we don't have any limitations on the number of attackers or any limitations on the mobility of the attacker. And there is no physical access, which is kind of common in even the older attack models. And another thing is that we call this a seamless takeover attack, which was also demonstrated in practice in southern waters north of Italy by Dr. Humphrey's group in UT Austin in 2013, where the attacker is not able to increase the power of the signal more than a certain threshold, because otherwise it would be an easy problem to solve using energy detectors. So there is a limitation on the power of the attacker. Well, there are a lot of solutions. In our group, we have had several contributions to solve for this problem. And on the bigger picture, the solutions are categorized into two groups. We have hardware-based approaches and we have software solutions. The main drawback of hardware solutions is that they usually require some additional device, and that imposes a cost that we are not really ready to take. And the other drawback is that usually these solutions are limited to GPS spoofing detection, but what happens afterwards? How do we recover from being spoofed? The software solutions are also sometimes not really backward compatible because they require modifications to the space segment side, and any modification to the space segment side is going to be like a multi-million solution. We really need to avoid that, and again, like spoofing detection, but what about recovery? These are the problems that we are trying to address in our contribution. Where we look into 5G new radio as a solution for this problem. We want to see how we can, if we can take advantage of the cellular technology. Like previously, before 5G, 4G was there, and because of the limited bandwidth, there was less accuracy, less resolution in the time domain. And if we used 4G for localization, the accuracy that we were able to achieve was around 50 meters. GPS and non-assisted GPS has accuracy of sub-meters, so this is not really, like if we recover the location today with error of 50 meters, we cannot really, this is not the best solution that we can do. But thanks to 5G, even in the sub-6 gigahertz, we have 100 megahertz of bandwidth that helps us to do multi-path recovery in the time domain, which with much better resolution, and that's why we are able to have more accurate estimations, and we will have sub 10 meter localization accuracy. This makes 5G sub 6 gigahertz a good candidate for the purpose that we want to use. These are simulations, like this is a simulation using 4G. So this we can see the actual location position of the user, and then this is the estimated one. So we can see, like if you look at the error here, it's up to 25 meters. When it comes to 5G, we are using some open source emulators, and if this is the actual location, this is the estimation, and it is like we can see the numbers are significantly reduced, and it is around the sub 10 meter accuracy. And the particular type of technique that we are using in both of the for both 5G and 4G is time difference of arrival, or TDOA. Well, there are many methods, so I'm not going to dig into the details, but the main advantage of using TDOA is that it solves for the synchronization problem, and that's why it is the more common one. So we do stick to the best solution that we can use. So eventually, going back to the GPS spoofing detection, this is a high-level illustration of what happens. So for a particular user, if there is a difference between the location using GPS and 5G, then we know that spoofing is ongoing. Otherwise, we are in a normal condition. But in practice, it's never that easy, because our measurements and our estimations are both error-prone. So we have, but GPS is already known as a very error-prone technology. And for 5G estimations, it's never perfect. So we're going to have, in an ideal situation, the distance in a legitimate situation would be 0. But this is not attainable in real life. So we need to find a way to handle these errors and distinguish between the two cases. This is then a snapshot of our measurements when we collect GPS data, and there is a localization solution in east-north down coordinate. And you can see the standard deviation of the estimation is kind of large, and this is going to affect how this method works. That being said, we look into real-life experiments. We collect data when there is no spoofing going on in normal condition. And this is showing the 5G solutions as well as the GPS-driven location solutions. So we can see that they kind of overlap, but obviously there is some difference. If we look into the discrepancy, like 5G minus the 5G-driven location value, then we can see that the difference is, it has significant value. We need to define a threshold, which in a normal condition, all of the data points fall below it. But obviously, like how aggressively you want to set that threshold is something to investigate. And we will, like if I have the threshold here, I will face false positives here. Moving on to the spoofing scenario. Here, there is no spoofing, and then when spoofing happens, we can see that the GPS solution kind of deviates from the 5G solution. And we need to set this threshold in a way that we avoid misdetection. So we're gonna be focusing on that, and on the other hand, like the trade-off is that we're gonna have false positives. That being said, we go to discussion, which is my favorite section. Well, this method is valuable because it doesn't impose additional costs, and it doesn't impose additional hardware. So because we are using the existing infrastructure, we're using the existing cellular technology, and we have high detection rate, and this method grows more robust as technology evolves. And also we are able to thwart both single attacks and coordinated attacks. And coordinated attacks are kind of underdeveloped in literature, and they are usually overlooked because there is no real-life implementation of them. There are limitations. The main limitation is the trade-off that I just talked about, is the false positive that we impose because we are choosing the threshold in a way that we do not have misdetections. And also, we really do rely on the 5G technology, so we need phones that are compatible with the 5G technology. And even when they are compatible, we need to have enough coverage. So there should be enough base stations, so the user can be able to solve for the 5G localization. Otherwise, this is not going to work. So as I said earlier, as technology evolves, this solution is going to be more robust because the main limitation was the measurement errors and the estimation errors. And if the hardware develops, when the theory develops, then this is going to be easier to handle. Also, we should really take the multi-attacker scenarios more seriously because there is no demonstration yet. But the only challenge in demonstrating multi-coordinated attacks is the synchronization. Which is not a very difficult problem to solve. And one last thing is that this method is kind of decentralized, which is why, like the user, if the user wants to take advantage of this method, they don't really need to transmit their location to a center. That's why we are not introducing additional privacy concerns. And I think privacy is a very hot topic, and if we need to think ahead and design solutions that don't really threaten the privacy of the users. Well, in summary, we tried to put forth an accurate and cost-free GPS spoofing detection and recovery methods, and we used 5G for that purpose. And we had some challenges, especially when it comes to falsing, but in future work, we are extending this one using some crowdsourcing method, and we also want to work on designing an offensive to try to break this. Thank you for your attention and questions.
Thank you. Questions? That was all new to me. Very interesting talk. Thank you. I didn't know that GPS spoofing existed. I learned a lot. You did mention that GPS is error prone, right?
Yes.
So couldn't cases like the Russian vessel that was 20 miles away, that couldn't be an error? That was necessarily a GPS spoofing?
20 miles is
a lot, okay.
Yeah, is more than the error is top 10 meters, but it's still like because we spoofer works is that it chooses a coordinate and you plug it into the software, and then it kind of transmits signals that if you solve using those signals, you're going to end up in that particular location. So the coordinate is the choice of the attacker. It was 20 miles away because the attacker wanted that to be 20 miles. It could be 40 miles away with no additional challenges.
Okay. Yeah, my question was more general. It was more in the sense that some of the things that we think are GPS spoofing, they could be due to measurement errors.
Yes, below 10 meters, it's very difficult to distinguish if it is non-assisted GPS.
Okay.
That's very true.